Okay. I'll tell you the truth, what is the title of this chapter? Interactions and implications. I'm going to look at the section title at least. Temperature. Okay, temperature. So we have talked about multiplicity of system, the number of ways it can arrange itself, which gives you a measure of the relative probability of finding the system in one microstate or another. All microstates are equally probable. The relative probability of finding the system in one macrostate or another. Remember, the macrostates correspond to things that we can practically measure about it. Its temperature, its volume, the number of particles, its energy, things like this. Those are macrostate properties. And we usually don't have an easy way of measuring the microstate properties because it's very small and they're just enormous numbers of these. So then we got to the entropy, which is Boltzmann's constant times the natural log of the multiplicity. We can just think of it being the log of the multiplicity. So it's a much easier way of scaling these probabilities. And the entropy, now, is what we're going to deal with most of the time. We briefly talked about how systems can exchange energy, or they can exchange volume, or they can exchange numbers of particles, and that there are equilibrium conditions under these exchanges when the exchange will stop. So, for example, and what we're going to do now is allow two systems to exchange energy between them, or two parts of a system, part A, part B. And when they exchange energy, they will exchange energy up until the point that they come to thermal equilibrium. Once they're in thermal equilibrium, the exchange stops. Now, I should say, it's not that there's no energy exchange once they're in equilibrium, but there's as much flowing one way as there is the other. So there's no net exchange anymore. Okay. We'll start off with two Einstein solids that are what we call weakly coupled. Weak coupling means that the exchange of energy takes place between sections A and B relatively slowly, but once energy gets into one of these solids, it's immediately dispersed throughout the material. And this is pretty close to accurate. Okay, so here we'll put A on the left and B on the right. They can exchange energy. So we'll have a number of particles be in A and in B. And again, as we've done a few times before with these Einstein solids, because the energy in them is quantized, then it's easy to keep track of the number of energy units, the quanta of energy units. Capital U is the energy, but lowercase q is the number of units of energy. And they're proportional to each other, so it's another way of counting it. So A has Q sub A units of energy, and B has Q sub B units of energy. And of course, they can exchange back and forth those units of energy, but the total will remain constant. So in this example, let's let okay, this is one example. A has 300 oscillators. B has 200 oscillators. And the total quanta of energy is going to be the sum of the amount held by A and B, which can shift. And that'll be 100 units of energy to be shared between the two of them. And again, I'll note there, a little equation for total. Okay. All of this is the same as we had back pages ago on page 58. We've got the same pair of Einstein solids we've done before. If you look on your book here, you'll see that he's got a table then of the multiplicity of each one of the macro states. We're going to measure the different states according to the amount of energy held by part A. Just we can pick either one, we'll choose A. If we look at the probability, the multiplicity rather, of the number of ways that we can have A have 0 units of energy, or 1 or 2 or 3 or 4 like that, all the way up to A having all 100 units of energy, and we'll be able to see that the multiplicity changes to these. Okay. Now let's see here. To calculate the multiplicities, let's recall the equation for the multiplicity of an Einstein solid with N oscillators and Q units of energy is Q plus N minus 1 factorial over Q factorial N minus 1 factorial. And that's equation 2.9. All right. Now to find the entropy, which is our new part. K log omega. All right, and that is equation 2.45. Now, the author has written out a table with all of the different numbers, all the different multiplicities, and their corresponding entropies for all of the different macro states, QA equals 1, 2, 3, 4, 5, 6, all the way up to 100. I'm not going to try writing the table down, it's a lot of lies. But here's a graph of the table. I think you'll agree it's easier if I plot the entropy rather than plotting the multiplicity. Much smaller numbers, easier to handle. So I will plot the entropy as a function of QA, the energy held by part A. Okay? Rather than plotting the entropy itself, to make the numbers easier, let me divide the entropy by K, which means I'm really simply plotting the natural log of the multiplicity. So why do that rather than just plotting S, 6 of one, half dozen of the other? But this makes it unitless, and just the numbers are slightly simpler to work with. So I'm going to plot S over K. Okay, so I'm plotting the log of the multiplicity. Now, because, if you look here, you see that A has more oscillators than B. The system is not symmetrical. It's more likely for A to wind up with a bit more of the energy here. So, if I plot this out, and this is where I really wish I had colored chalk in here, maybe we'll get some. The entropy per K, starts off here, if QA is 0, and here it's 100, the peak, let's see, it starts off rising rather steeply. And it reaches its maximum at QA equals 100. Oh, sorry, this is the entropy of part A, just of A. Let's see, how should I label it? Maybe I'll just put an A next to it. There we go. If I were to plot the entropy for part B of the system. Now, if A has all the energy, B has none. And if A has no energy, B has all of it. So I could plot this just as easily versus Q sub B. If I know QA, then I know QB. The entropy for part B is 0 when A has all the energy, and it rises rather steeply. And it flattens out as it goes up all the way over to the left-hand side. Notice that the highest amount of entropy that part B can have, let me label it again, is less than the maximum entropy of part A, because it has fewer oscillators. Let me also plot the total entropy, the sum of A and B. So that's the total entropy of the entire coupled system. If all I have to do is add these two numbers, okay, that's the dashed line, is the total entropy. Now, the total reaches a maximum when A has 60 units of energy. And that's just a matter of, you have to calculate the numbers to find that out. But in this case, if A has 60 units of energy, that's where the total entropy of A and B together is the maximum. Okay. So, see what we've got here. If we were to have the system in a state where A had very little energy, over here on the left-hand side, and B had a lot of energy, sorry, plotting this way. So if A has very little, we're over here. Notice that the entropy as a function of energy, this is what this is a plot of entropy as a function of A's energy. Over here on the left-hand side, if A has very little energy, the slope of its entropy graph is steep. But B has a shallow slope, and of course tilting the other way. On the other hand, when A has a lot of energy, let's see, well, it's the other way around. But the important thing is, if you have a shallow slope, if B has most of the energy, it's got a higher temperature, right? Number of energy, amount of energy per oscillator is high, the temperature is high, and the slope here is shallow. Down here, A has very little energy, but it has a very steep slope. Its temperature is low, the slope of entropy versus energy is steep. So a shallow slope corresponds to a high temperature. Steep slope corresponds to a low temperature. And what happens? If you put the system in this arrangement, energy wants to flow from the one at high temperature down to the one at low temperature. So this is the flow of energy is that way, from B to A. The one with the shallow slope down O to the one with the steep slope. Now, that flow of energy will continue until you get to here. Look here where the total entropy peaks. At this point, okay, the slope of the total entropy line is flat. And at this point, A and B have the same slope, although in opposite directions. So they have the same temperature. And there's no net flow of energy at that point. They're at thermal equilibrium. I'll derive this mathematically now. Okay, so recall that an equilibrium state is the most likely state. There. Where the total entropy is the highest, that means your total multiplicity is the highest. That means the system is in the most likely state it can be in. That is an equilibrium state. That means that the total multiplicity, and therefore, because entropy is the log of multiplicity, the total entropy are at their maximum. If the total entropy is at a maximum, the slope of entropy versus energy is 0. At a maximum point, the slope has to be 0. This is just straight from calculus. So, therefore, let's see here. The slope, the derivative of total entropy as a function of the energy held by system A is 0. Now notice what I've actually written down. I've written this down as a partial derivative. Okay, so I've got the curled D's here. Remember that a partial derivative is simply when we assume that all the other variables are constant. We're only worried about the total entropy as a function of QA, and we assume that every other variable is a constant. And we don't have to worry about the derivative with respect to that. Okay, so that's what these are here. Partial derivative of total entropy with respect to the energy held by A is 0, and that means that's the slope is horizontal, and that tells us we're at maximum. Now, in practical terms, we don't actually, it was easy to plot this way, but in practice it's better to be working with the measured energy, U, rather than the number of units of energy, Q. So, recall that the energy, capital U, is the number of quanta of energy times Planck's constant times the frequency of the oscillation. This is for a simple harmonic oscillator in quantum mechanics. Okay, so this also means, because the energy U is proportional to the number of quanta of energy, we're really just rescaling how we measure the energy. And let's write this the normal way. The partial derivative of total entropy with respect to the energy of part A is 0 at equilibrium. That's going to be our key thing. So, working with that then, the total entropy. But really we've got two parts of it. The total entropy, we remember, is simply the sum of the entropy of each of the parts. Right? Yes, that's true. So, we'll take this and we'll put in that the total entropy is SA plus SB. Okay? Total is A plus B. Well, we've got the derivative of the sum of two functions. Well, that's just the sum of the derivative of each of those. So, partial of SA, partial derivative of SA, with respect to UA, plus the partial derivative of SB, with respect to UA, is 0. All fine and dandy, but the first part of this is straightforward enough. We're taking the derivative of A's entropy with respect to A's energy. But on the second part, we're taking the derivative of B's entropy with respect to A's energy, and that's a little awkward. Luckily, think here for a second and realize that the total energy is constant. We've isolated the system from the rest of the universe, so the total energy is constant. And the total energy is the sum of the energies of A and B. I need to go one more click over here. Okay. So, solve for, I've got UA here, and I'd really like to have UB in there. UA is just U total minus UB. Okay. What I've got here is the derivative of S with respect to UA. Well, in the denominator, that's the differential of energy A, a small change in energy A. So if I take the differential of both sides here, let's see here, that means du sub A is equal to, du sub A is equal to du total minus du sub B. If UA equals U total minus UB, then the differential of UA, small change in that, equals small change in U total minus a small change in UB. How much can the total energy change? If it's constant? None at all here. The total energy can't change, because we said it's constant. So that means any change in the energy held by A is negative of the change in the energy held by B, which is kind of obvious when you think about it, but we've actually just proven it now mathematically, which lets us slip it into the equation. Okay, that means that dsB by dUA is negative dsB by dUB. I just put, for dUA, I put in negative dUB. And I can pull that negative sign out front there, and I'll continue on the next chalkboard. which means there. I just add dSV by dUV to both sides, and I find that at equilibrium, the slope of the entropy of A with respect to the energy held by A is the same as the slope of the entropy of B with respect to the energy held by B. And that graph that I showed then, I plotted it all in terms of the energy held by A. But that means that the slopes will be the same slope, but of opposite sign, if I'm just looking with respect to A, when they're at equilibrium. Now, this is an important result here. The derivative of S with respect to U is the same for each one of the parts when those parts are in thermal equilibrium. This all happens spontaneously, just by the exchange of energy. So what I've got here is really a statement about the temperature. We know that the heat will spontaneously flow from the hotter to the colder object until they reach the same temperature. That's when they're in thermal equilibrium. How does the heat flow? Well, it's the spontaneous transfer of energy from one to the other, which is just what the situation is that we've set up here. So, if the temperatures are the same when they're in thermal equilibrium, and the derivative of entropy with respect to energy is the same when they're in thermal equilibrium, this is probably a measure of temperature. These slopes are a measure of temperature. But, does that mean that ds by du is the temperature? Take a look at the graph again. Let me swing it around. And I'll zoom in here. This will work again. Okay. The one that has less energy has a steeper slope. It's got less energy per oscillator, it's got a lower temperature. As the energy goes as the energy per oscillator, per particle, whatever. So really the slope here is 1 over the temperature. It's the inverse, the reciprocal of temperature. Energy is flowing from the shallow slope to the steeper slope. All right, so I'm going to propose that we define temperature as the inverse of this slope here. So 1 over temperature is partial derivative of entropy with respect to energy. And in fact, we'll make that's a triple equal sign, that's a definition there. This is going to be our theoretical definition of temperature. Now, actually I should modify this just a little, because I've got a partial derivative here. That means that other variables are held constant. In particular, it means that the number of particles and the volume are constant. So I put those as subscripts after the partial derivative. This notation means partial derivative of S with respect to U when N and V are constant. Okay. By the way, isn't it just mathematically a little awkward to have to deal with this derivative is 1 over the temperature? Remember what a derivative is. A derivative is a ratio of small changes. This is the ratio of small change in S divided by small change in U. Well, That means that if I cross multiply, that would be the same as temperature equal to du divided by ds, the partial derivative of u with respect to s when number and volume are held constant. Mathematically, isn't this the same thing? Yes. Assuming you're not dividing by 0, which in practice we will not do. So why don't we just do this? Because, I mean, we could, but in practice, in many cases, most cases, maybe all cases, not really sure, we may have a function written out for entropy as a function of energy, where it's easy to take the derivative of entropy with respect to energy, s with respect to u. It would be much more difficult to solve that function to find u as a function of s in order to do this derivative. This is perfectly true, but in practice it would be difficult to do. Just keep that in mind. So we'll generally have s as a function of u. We plug it in there, take the derivative, we've got 1 over temperature. As an example on numbers. Let's see here. For the table he has on page 86, table 3.1. If you've got a table of numbers, and you've got entropy and you've got energy calculated for each of the possible states there, then you can actually do the derivative yourself numerically and get a pretty good number for this here, in a small enough system like this. So in fact, this would be easy enough to do in the example we've done, because we have u and we have s and we can make small changes. So in our particular example, we can write out, let's see, move this over. And let's see what kinds of numbers we get for this. All right, where is the equilibrium? How many quanta of energy? Let's see. Actually, if we look, it might be difficult to do. If we, no, I think we could do this. If we have, he gives an example if part A has, in the interval around 12 units of energy. But that's not an equilibrium. I'm kind of curious. He doesn't do the example, but what is the equilibrium temperature? Actually, he does that as a homework problem, doesn't he? 3.1. Let's just do it here. Find out what's the equilibrium temperature of this system. Equilibrium occurs when A has how many quanta of energy? Look at the graph. 60. Okay. Let's find the temperature. We'll find the temperature of A and the temperature of B, and we'll show, by the way, that they're basically the same. Okay. So what we want is, if temperature is the ratio of du by ds, 1 over temperature is ds by du, and we can do it numerically here pretty easily. If you have discrete changes in things, we can make that as delta u divided by delta s. So we want to look at a change in the energy where the energy is right at QA equals 60. So if we take, say, 61, the change when the energy changes from, say, final minus initial, so 61 units down to 59 units, that brackets right around that. So U equals QFH, QHF, so we've written it. And he suggests writing it out where HF, this is again from quantum mechanics, let's just call that epsilon. This is a unit of energy, HF. An individual quantum of energy has that much. And then we'll plug in an amount for what that might be in just a moment. So delta U would be delta Q epsilon. Epsilon is a constant. And let's see. Okay, take a look then. If we have delta Q go from 61 down to 59, okay, the change in the entropy would be from, let's see, he gives it to us in terms of S over K, so we'll have a factor of K out front. Boltzmann's constant. So that's 160.9 minus 157.4. Okay, so we have epsilon over K times, what are the numbers here in the numerator and the denominator? We need calculators for this.
We're not calculating an E or K.
Not yet.
.57.
0.67,
57.
0.57, 0.57 epsilon over K. Okay. Now, if that's the case then, what we need to do, Boltzmann's constant we just look up in the front cover of the book. Epsilon, we need to say, well, that depends on what the system really is. It could be an Einstein solid with very large gaps of energy between each level, or it could be very small ones. And he picks a system where the energy quanta is at the level of 1/10 of an electron volt. Take a look on page 88, it shows that there. So, if we pick that, and Boltzmann's constant in the front inside cover of the book can be given in terms of electron volts per degree Kelvin. It's 8.617 times 10 to the minus fifth EV per Kelvin. then the temperature of A is 0.57 times 0.1 electron volts divided by 8.617 times 10 to the minus fifth eV per Kelvin. Electron volts cancel out, and I'm going to need some help with the calculator here. We'll wind up with Kelvin, 0.57 times 0.1, all divided by 8.617 times 10 to the minus fifth.
That's 663.
653?
663.
663?
That sound right?
Sounds pretty reasonable. I don't actually know the answer. But he calculates it for A having a small amount of energy, therefore a low temperature in the book, and comes up with A having a temperature of about 360 Kelvin when it's at low temperature. Here, when it's at equilibrium, it would have to be at a higher temperature. And that makes sense that it could be about like that. So this sort of shows you, remember 300 Kelvin is room temperature, give or take a little bit. 600 Kelvin is hot, but you're not getting up to, temperature of the star. The sun, for example, is at 6,000 Kelvin. So we're still on Earth-type temperatures that you could find in a, I'm trying to think, not a stove really, but in a small furnace or something like that. We're used to get to that temperature. Okay. Understand what's going on here? Now, again, what we just did was we applied this temperature as du by ds when everything else is constant, but our more practical one in most cases will be that 1 over temperature is ds by du, because we will generally have a formula for s as a function of u. In this case, we happen to have a table of both s and u, and that allowed us to calculate it numerically the other way around. Okay. I'm going to go over his example of an analogy, kind of verbal analogy to temperature and entropy. This eraser has seen better days. Okay. Because of the implications of how entropy works, it's often helpful to have some analogies for it. This one kind of works. You can make a comparison with, you can sort of anthropomorphize the systems in a way to describe what entropy is really doing. And he says that imagine a world in which people exchange money in attempts to become happier. By the way, this is actually not as far-fetched because in some branches of economics, they've taken to applying what are basically the laws of thermodynamics to economic systems to model how they how people act in certain ways. And you wind up with things which, first, second laws of thermodynamics, wind up getting applied as analogies in economics and making some interesting studies there. So this area is called econophysics, which has got a whole little sub-discipline of its own. Okay, so imagine people are exchanging money in attempts to become happier. I don't know, we can see that happening plenty. They're not merely interested in their own happiness in this analogy. Each person is trying to maximize the total happiness of everyone in the community. So you've got some amount of altruism going on. Now, some people vary on what kind of behavior they've got. Some people become much happier when they have only a little more money. Or, let's see, when they're given just a little money. These would be the greedy people, because they'll accept money very gladly, and they're very reluctant to give it away. Other people become just a little bit happier when they're given more money, and they're not very sad when they lose some. These would be the generous people. They're not too unhappy giving money away, and it maximizes the total happiness there. So the analogy works where the community is a system of objects. The people correspond to various objects in the system. The money is the energy. So, exchange of money is equivalent to the exchange of energy. The happiness then is the entropy, because the system, thermodynamic system, tries to maximize its entropy, and by exchange of energy. And the generosity of any member of the community would correspond to the temperature. This is that last one is the trickier one in concept. Generosity corresponds to temperature. This is the measure of how willingly someone gives up money or energy. Okay, now he says, going a bit farther with the analogy, normally you expect that as people get more money, they become more generous in just a run-of-the-mill kind of behavior. In thermodynamics, this is meaning that as an object's energy increases, so does its temperature. If people become more generous when they get more money, and again, we're not making any real strict comparison with morality or anything, but as you can expect that they're more willing to give away a few dollars if they've got a whole lot themselves, a thermodynamic system becomes more willing to give up some energy if it's at a higher temperature. Most objects behave this way. Increasing temperature corresponds to a decreasing slope of entropy versus energy, so that the graph is concave down. So the normal graph entropy versus energy for a normal system is like that. Concave downwards, but increasing. As energy goes up, the entropy goes up. But it's concave downwards. Okay, so remember that as it gains energy, its entropy goes up. And its temperature, its generosity, its willingness to give up some of that energy increases as well. Temperature, this is the thing that's a little tricky. Temperature is 1 over this slope. its temperature is lower here, steep slope, and the temperature is higher here, shallow slope. In the analogy, the generosity is very low. You're kind of, you're not wanting to give up much money if you don't have much. But you're much more willing, shallower slope, to give up money if you've got a whole lot in this way. Okay, but there are some systems, some kinds of people, who are different. If they get more money, they are less willing to give it up. Misers. These are ones where, sure, as they get more energy, they have a higher entropy, but they're less willing to give that energy up. Concave upwards. The slope, 1 over the generosity, 1 over the temperature, increases as they get more energy. So this kind of a system would be less willing to give up energy when it has more. A normal system is more willing to give up energy when it has more. Now, to press the analogy to the last point then, you have some who have achieved enlightenment, and as they get more energy or money, they are actually less happy with the whole thing. Using his term, this the enlightened one here. But the more money they've got, the less happy they are with it. Okay, let me make sure I've got the slope correct. So this kind of a thermodynamic system doesn't even want to gain energy at all. It wants to lose energy. Let's see. That says this is a very counterintuitive kind of a system, but it does occur in some cases. One interesting thing on the miserly systems here. While a normal system would include a gas, a normal gas that we deal with in the lab, if you have a collection of particles bound together by gravity, it's this miserly system here. So when gas collapses under its own weight out in space and forms a star, or when stars fall in towards each other, form a galaxy, it's bound together by the mutual gravitation. It behaves this way. And this has some really strange consequences. You get negative heat capacities, you get, there are a number of things. Temperatures change in an odd way with this. But we'll get to those, I will get a few of those cases. Okay. And I think this will be a good ending spot there.